New York, November 1966. Temperatures hover near 4 degrees Celsius. The wind is almost completely still. What begins as a clear holiday weekend quickly begins to change. A dense yellow-brown smog starts to settle over the 5 boroughs. By Thanksgiving afternoon, visibility drops to less than 1 mile, or 1.6 kilometers. The Thanksgiving Day parade continues as planned, but the air is thick and acidic. People begin to report burning eyes and a bitter metallic taste in their mouths. And this is only the beginning. Over the next 4 days, we will break down how a combination of weather patterns, high sulfur fuels, and heavy reliance on private automobiles created a deadly atmospheric trap. We will follow the timeline of the crisis step by step and examine how the city's health system came close to collapse. If you are listening right now, write in the comments where you are from and what time it is for you. It is always interesting to see where these stories are being heard. If you enjoy this calm and analytical format, consider subscribing. Here, we explore real historical events with clarity and depth. This is not a fictional reconstruction. This is the real story of the poisoned city. At 12 p.m. on Sunday, November 20th, 1966, a massive high-pressure cell began to stall over the eastern seaboard. This atmospheric mountain of air covered over 1,000 miles, 1,600 kilometers, of the coast. By Monday morning, the barometric pressure at the New York Weather Bureau reached 30.20 inches, 1,022 millibars. Under normal conditions, the atmosphere works like a giant chimney for a city. The sun warms the ground, which then warms the air directly above it. This warm air is less dense than the cold air in the upper atmosphere. It naturally rises, carrying the city's dust and exhaust high into the sky. In a healthy system, this vertical movement allows for constant cleaning. Meteorologists call this the adiabatic lapse rate. It is the predictable cooling of air as it moves higher into the sky. For every 300 meters, 984 feet, of altitude, the temperature usually drops by about 2 degrees Celsius, 3.6 degrees Fahrenheit. As long as this gradient exists, the air remains in motion. On November 21st, the National Meteorological Center in Maryland observed a change in this pattern. The high-pressure system was no longer moving toward the Atlantic. It had become a stationary anticyclone. Inside this system, a phenomenon called subsidence began to occur. Millions of tons of air started to sink slowly toward the Earth. As this air descends, the increasing pressure causes it to compress and grow warmer. By Tuesday afternoon, this sinking warm air met the cooler air resting over the Atlantic coast. The natural temperature gradient was suddenly flipped upside down. Instead of getting colder with height, the air actually became warmer. A layer of air at 600 meters, 1,968 feet, was now warmer than the air at ground level. This created a thermal inversion layer. It acted as a physical barrier that prevented any vertical movement of gases. At 3 p.m. on Tuesday, November 22nd, the lid was officially in place over Manhattan. The mixing depth is the height to which pollutants can rise and disperse. Usually, this depth in New York is over 3,000 feet. By the evening of November 22nd, the mixing depth plummeted to less than 600 feet. The city was effectively capped by a ceiling of warm air. There is a quiet absurdity in how the most stable weather can become the most lethal. While the sky appeared clear and the winds were calm, the city was being sealed in a jar. The geography of New York City worsened the effect of the inversion. The city is surrounded by the Hudson River, the East River, and the Atlantic Ocean. These bodies of water kept the surface air cool and damp. At 8 a.m. on Wednesday, November 23rd, the temperature at ground level was 7 degrees Celsius, 45 degrees Fahrenheit. However, the layer of air just a few hundred feet above was nearly 13 degrees Celsius. This temperature difference meant the air at the bottom was too heavy to rise. It became stagnant and trapped between the skyscrapers. Horizontal wind speeds also began to fail. The prevailing winds dropped from 12 miles per hour, 19 kilometers per hour, to less than 4 miles per hour, 6 kilometers per hour. Without horizontal or vertical movement, the air over the 5 boroughs became a closed system. Technical reports from the Weather Bureau indicated a stagnation index of over 12 points. Any reading above 8 points suggests a high potential for air pollution. Meteorologists at the top of the RCA building could see the horizon disappearing. Visibility at LaGuardia Airport dropped to 3 miles, 4.8 kilometers by Wednesday afternoon. This was not caused by clouds or rain. It was the result of a thickening haze that had nowhere to go. The inversion layer was not just a local event. It stretched from Maine down to Virginia. However, the density of the urban infrastructure in New York made it the epicenter of the trap. The atmosphere had stopped functioning as a filter and had become a reservoir. Every pound of matter released into the air was now staying in the air. The chemical composition of the atmosphere began to shift away from oxygen and nitrogen. This stagnation occurred exactly as millions of people prepared for the Thanksgiving holiday. As the sun set on November 23rd, the barometric pressure remained high and the air remained still. The weather had set the stage for a disaster by simply refusing to change. All that was missing was the massive volume of waste that a modern megacity produces every hour. This invisible lid was now waiting to be filled with the byproduct of 1 million furnaces. As residents turned up their heat against the November chill, they were unknowingly pumping poison into a room with no ventilation. The trap was set, and the city was about to provide the fuel. At 6 p.m. on Wednesday, November 23, 1966, the temperature in Central Park fell to 40 degrees Fahrenheit, 4 degrees Celsius. As the Thanksgiving holiday approached, the demand for residential heating across the 5 boroughs surged. New York City in the mid-1960s was an industrial giant that functioned on a diet of high-sulfur carbon. The city relied on a massive, aging infrastructure designed to burn the cheapest fuels available. Unlike modern cities that utilized natural gas or renewables, the New York of 1966 was powered by coal and heavy residual oils. The primary architect of the city's energy was Consolidated Edison, known commonly as Con Edison. By late November, the utility company operated 11 major power-generating stations within the city limits. These plants were concentrated along the East River and the Hudson River. The Ravenswood plant in Queens and the Waterside plant in Manhattan were among the largest. During the peak hours of Wednesday evening, these stations operated at near maximum capacity. To meet the electrical needs of 8 million people, these plants burned massive quantities of bituminous coal. New York's energy system was a hierarchy of heavy fuels. At the base was No. 6 fuel oil, also known as Bunker C. This was a thick, viscous byproduct of the petroleum refining process. It was so dense that it required preheating just to flow through pipes. Because it was a residual product, it was inexpensive and widely used for both electricity and heating. However, this cost-saving measure came with a high environmental price. There is a dark irony in a city burning itself to stay warm, while the very heat it generates seals its fate. The energy plants followed a simple but dirty mechanism. Coal and heavy oil were fed into giant boilers to create steam. This steam turned turbines to generate electricity for the subway system and the skyline. In 1966, the technology for scrubbing or filtering exhaust was almost non-existent in urban plants. Whatever entered the furnace as fuel exited the smokestack as gas and ash. Under the inversion lid, these stacks were no longer venting into the atmosphere. They were pumping directly into a stagnant, low-level reservoir of air. Beyond the power plants, the city's residential heating system added a second layer of pollution. Approximately 17,000 apartment buildings in New York utilized on-site boilers burning No. 6 oil. These systems were often poorly maintained and operated at low efficiency. Furthermore, New York possessed a unique and problematic system for waste management: apartment house incinerators. Nearly 30,000 buildings were equipped with internal incinerators for trash disposal. Instead of hauling garbage to landfills, residents dropped refuse down chutes directly into basement furnaces. On the night before Thanksgiving, as families prepared large meals, the volume of waste increased significantly. Thousands of these small fires burned throughout the night. They released plumes of thick, black smoke and fine particulate matter into the street-level air. The technical danger of the 1966 smog was not just the smoke itself. It was the chemical composition of the fuels. The No. 6 fuel oil used in 1966 contained between 2.5% and 3.0% sulfur. The coal used by Con Edison averaged 2.0% sulfur. When these fuels burned, the sulfur oxidized to form sulfur dioxide. This is a colorless gas with a pungent, suffocating odor. In the damp, stagnant air of the inversion began to react with water vapor. This process created a fine mist, or sulfuric acid, which hung suspended in the air. Data from the New York City Department of Air Pollution Control showed a spike on Wednesday night. Sulfur dioxide levels, which usually averaged 0.10 parts per million ppm, began to climb. By midnight, sensors in Harlem and Midtown recorded levels approaching 0.50 parts per million. This was 5 times the normal concentration. Along with the gas, the air was filled with particulate matter, or soot. These were tiny carbon particles coated in heavy metals and acidic compounds. While the boilers and power plants provided the base load of the smog, the transport sector provided the catalyst. The mid-1960s represented the peak of the post-war American car boom. New York City saw an influx of over 1.5 million vehicles daily. These cars used leaded gasoline and lacked any form of emission control, such as catalytic converters. As commuters left the city for the holiday on Wednesday afternoon, traffic gridlock became a source of concentrated chemical output. Idling engines produced high volumes of carbon monoxide and nitrogen oxides. In the still air, these gases did not dissipate. They stayed at bumper height, mixing with the falling soot from the apartment chimneys. The city was no longer just a collection of buildings. It had become a giant chemical reactor. The combination of industrial coal, residential oil, and automotive exhaust had filled the volume of air beneath the inversion layer. By the early hours of Thursday, November 24th, the interaction of these systems had reached a critical mass. The economic growth of the city had outpaced its atmospheric capacity. The reliance on high-sulfur fuels was an accepted norm of the era's urban economics. Cheap energy was the lifeblood of the megacity, and the sky was treated as an infinite sewer. As the sun rose on Thanksgiving morning, the festive atmosphere was masked by a deepening yellowish gloom. The mixing depth remained trapped at 600 feet, 182 meters. The emissions of the previous 12 hours had nowhere to go. New York was now fully immersed in its own waste. The holiday celebrations were about to be met with a deadly, motionless silence that would define the coming days. At 12 a.m. on Thursday, November 24th, the wind speed across the 5 boroughs dropped to exactly 0 miles per hour. The massive high-pressure system was now perfectly centered over the tri-state area. This created a state of total atmospheric stagnation that lasted through the early morning hours. By 2 a.m., the temperature at ground level had fallen to 45 degrees Fahrenheit, 7 degrees Celsius. However, the layer of air at 600 feet, 183 meters, remained significantly warmer. This thermal barrier prevented the heat and exhaust from the city's midnight activities from rising. The city was now a silent basin where the weight of the atmosphere held every molecule of carbon in place. Under normal circumstances, a holiday weekend provides a reprieve for urban air quality. Most heavy industrial factories shut down their assembly lines for the Thanksgiving break. Millions of commuters stay home, which drastically reduces the daily nitrogen oxide output from passenger vehicles. In 1966, city officials expected this holiday lull to naturally clear the darkening skies. However, this assumption failed to account for the physical reality of the inversion lid. The pollutants that had accumulated on Wednesday evening did not disappear. Instead, they simply sat in place and became more concentrated as new emissions were added. At 4 a.m., the residential heating systems across Manhattan and Brooklyn began their morning cycle. Despite the holiday, the 17,000 large apartment boilers continued to burn number 6 residual fuel oil. This heavy oil maintained the internal temperature of the city's aging housing stock. Each boiler pumped more sulfur dioxide into the air at a height of only 50 to 100 feet, 15 to 30 meters. Because there was no wind, these plumes of smoke did not drift away. They mushroomed outward and merged with the smoke from neighboring buildings. There is a quiet tragedy in how a day of rest can become a period of peak vulnerability. The very buildings meant to shelter the population were now flooding their lungs with invisible toxins. By 8 a.m., the technical sensors at the Davis Island Weather Station recorded a terrifying shift in air chemistry. The coefficient of haze, or COH, is a measurement of how much light is blocked by solid particles in the air. A normal, healthy COH reading for New York is usually below 1.0. On this Thanksgiving morning, the reading jumped to 4.5 in parts of the Bronx and Harlem. This indicated that the air was 4 times more opaque than usual. Visibility at Central Park was reduced to approximately 1 mile, 1.6 kilometers. The sun appeared as a pale, sickly disk of white light that struggled to penetrate the thickening yellow-brown haze. At 10 a.m., the Macy's Thanksgiving Day Parade began its march down Central Park West. Over 1 million spectators lined the streets to watch the giant balloons and festive floats. Most of these families were unaware that they were standing in the highest concentration of pollutants recorded that year. The parade itself contributed to the crisis. Hundreds of internal combustion engines from the floats and support vehicles idled for hours in the stagnant air. This added a fresh layer of carbon monoxide and lead to the street-level environment. Spectators reported a metallic taste in their mouths and a burning sensation in their eyes. Many assumed it was simply the cold November air. Technical logs from the Department of Air Pollution Control showed that sulfur dioxide levels hit 0.51 parts per million, ppm, at noon. In modern standards, this would trigger an immediate emergency evacuation, or stay indoors order. In 1966, the city's alert system was still in its infancy. The officials monitored the numbers but did not yet have the legal power to stop the parade or close the streets. The interaction of the stagnant weather and the holiday routine created a perfect trap. The people were outside in record numbers, exactly when the air was at its most dangerous. By 2 p.m., the chemical saturation of the lower atmosphere had reached a critical threshold. The moisture in the air from the nearby rivers began to cling to the soot particles. This created a dense, greasy fog that felt heavy to the touch. It coated the windows of department stores and the lungs of the holiday crowds. The holiday reduction in office activity had been completely offset by the accumulation of residential and parade-related waste. The system was no longer purging any of its intake. It was only storing it. As the afternoon light began to fade, the air quality did not improve. The inversion layer remained firmly at 600 feet, 183 meters. The nitrogen oxides from the morning traffic had now spent hours reacting with the limited sunlight. This was creating a secondary layer of photochemical smog. The holiday was ending, but the chemical reaction was just beginning its most volatile phase. The city was now breathing a cocktail of gases that the human body was never designed to process. This mixture was preparing to move from the streets into the clinics and emergency rooms of the 5 boroughs. The silence of the stagnant air was about to be broken by the sound of sirens. The physical buildup of the smog had reached its limit. Now, the biological impact on the citizens of New York was ready to manifest. By 6 p.m. on Thursday, November 24th, the air over New York had reached a state of chemical saturation. The atmosphere was no longer a transparent gas. It had transformed into a complex, suspended aerosol. This mixture was a direct result of high-sulfur fuels burned during the previous 24 hours. Under the inversion layer, these chemicals were trapped in a volume of air about 600 feet or 183 meters deep. The primary component of this toxic mixture was sulfur dioxide. At this hour, monitoring stations recorded sulfur dioxide levels of 0.60 parts per million. This gas is a byproduct of burning bituminous coal and heavy fuel oil. When sulfur dioxide enters the atmosphere, it does not remain stable. Inside the moist and stagnant air of the inversion, it undergoes a rapid chemical change. The gas molecules interact with water vapor and oxygen in a process known as oxidation. This transforms the sulfur dioxide into a fine mist of sulfuric acid. There is a chilling precision in the way chemistry ignores human holidays. While families finished their dinners, the air outside was turning into a corrosive acid. This acid mist was not the only danger. It worked in a deadly partnership with particulate matter. Particulate matter, or soot, consists of tiny solid grains of unburned carbon and fly ash. These particles were often smaller than 5 micrometers, or about 0.0002 inches in diameter. In the stagnant air, these particles acted as transport vehicles for the acid. This is known as a synergistic effect. The liquid sulfuric acid would coat the solid soot particles. When a person inhaled, these coated particles traveled deep into the lungs, bypassing the natural filters of the nose and throat. Once inside the alveoli, the acid began to irritate and damage delicate lung tissue. The solid ash also contained traces of heavy metals, such as vanadium and nickel. These metals acted as catalysts, speeding up the production of even more acid within the lungs. At 8 p.m. on November 24th, carbon monoxide levels began to peak in Midtown Manhattan. Carbon monoxide is a colorless and odorless gas produced by the city's 1.5 million cars. Under normal conditions, it rises and dissipates into the upper atmosphere. On this Thanksgiving evening, the gas remained trapped at street level. It reached concentrations of nearly 20 parts per million in areas with heavy traffic. The danger of carbon monoxide lies in its interaction with human blood. When inhaled, it binds to hemoglobin about 200 times more effectively than oxygen. This prevents the blood from carrying oxygen to the heart and brain. For a healthy person, this can cause headaches and fatigue. For those with existing heart conditions, it creates a state of internal suffocation. The city was effectively experiencing a slow and collective poisoning that no one could see or smell. The chemistry of the smog also included nitrogen oxides. These gases are produced by high-temperature combustion in power plants and car engines. Even weak November sunlight at 12 p.m. triggered a photochemical reaction. Ultraviolet rays interacted with these gases and led to the formation of ground-level ozone. Ozone is a powerful oxidant that damages rubber, fabric, and human respiratory tissue. By 10 p.m., the chemical cocktail was complete. The air contained a mixture of sulfur gases, nitrogen oxides, carbon monoxide, and various hydrocarbons. These hydrocarbons came from unburned gasoline and industrial solvents. In the still air, they began forming complex compounds known as peroxyacetyl nitrates. These substances were responsible for the intense eye irritation reported by thousands of New Yorkers that night. The density of the air was now measurable through its effect on physical objects. The sulfuric acid began reacting with materials in city buildings. Limestone and marble structures started to experience microscopic surface damage. In the garment district, the acid mist was strong enough to damage nylon stockings worn by pedestrians. This was not a simple fog. It was a chemically active environment, slowly affecting both the city and its inhabitants. The interaction of these substances created cumulative stress on every living system. Sulfur dioxide caused the bronchial tubes to constrict. Carbon monoxide reduced oxygen supply to the heart. Ozone and related compounds irritated the eyes and throat. Each chemical reinforced the effects of the others. It was a multi-front assault on human biology. Air quality measurements were now exceeding all known safety limits of the time. As the clock struck 12 a.m. on Friday, November 25th, chemical concentrations reached their highest point. The city had spent 36 hours breathing inside a sealed atmospheric container. The air was saturated. Every breath contained millions of acidic particles and toxic gases. The invisible threat was now shifting from a chemical problem to a medical crisis. The reactions in the sky were nearly complete. The reactions in the city's hospitals were just beginning. The haze was no longer just a weather report. It had become a thick yellow-brown layer slowly covering the Manhattan skyline. At 5 a.m. on Friday, November 25th, the visibility in Central Park dropped to 150 meters, 500 feet. The city had vanished into a thick, oily fog that eyewitnesses described as dirty wool. This was not the typical white mist common to the Atlantic coast. The air had taken on a distinct yellowish-brown hue due to the high concentration of nitrogen dioxide. This specific compound absorbs blue wavelengths of the light spectrum. As a result, only the longer yellow and red waves reached the eyes of the residents. The physical process that turned the air into a heavy blanket is known as scattering. Solid particles of soot and ash in the air had a diameter comparable to the wavelength of visible light. This caused an intense scattering of sunbeams in every direction. Light no longer illuminated the streets, but instead created a dull, murky halo around every street lamp. By 8 a.m., the sky over Manhattan was the color of burnt ochre. The sun appeared as a faint white spot, stripped of all its warmth. There is a quiet absurdity in a city that built its identity on reaching the clouds, only to find the clouds had descended to swallow the pavement. At LaGuardia Airport, the situation became critical by 7 a.m. Air traffic controllers recorded a visibility drop to less than 100 meters, 330 feet. Pilots could not see the runway lights even from the end of the tarmac. By 9 a.m., the Port Authority announced a total suspension of all flights. At John F. Kennedy International Airport, visibility fluctuated near 200 meters, 650 feet. Planes bound for New York were diverted as far as Boston and Philadelphia. Tens of thousands of travelers were stranded in terminals, breathing the same toxic air that seeped through the building ventilation systems. Maritime traffic in the New York harbor was also paralyzed. Staten Island ferry captains were forced to reduce speeds to a crawl. They navigated solely by the rhythmic, mournful sound of foghorns. Sound travels strangely in heavy, damp air, becoming muffled and short. On the Hudson River, massive cargo ships dropped anchor to avoid collisions in the narrow channels. The river, usually a bustling artery of commerce, turned into a silent, gray void. On the city streets, pedestrians began using handkerchiefs as makeshift filters. Eyewitness accounts from that morning describe a taste in the air like burnt rubber and rotten eggs. This was the pungent scent of sulfur originating from thousands of coal furnaces and boilers. Many residents reported that their clothes and hair began to smell like smoke after only 10 minutes outside. The brown haze was not confined to the outdoors. It penetrated apartments through closed windows and door frames. Inside homes, visibility also began to fade, creating a sense of permanent twilight in living rooms across the boroughs. Technical data from the Department of Health laboratories confirmed the scale of the disaster. The concentration of suspended particulate matter reached 800 micrograms per cubic meter. This was more than 3 times the acceptable limit of the era. This solid dust settled on the mucous membranes of the eyes and throat, causing immediate and painful irritation. Applications for eye drops in city pharmacies rose by 400% by mid-morning. Despite these signs, the city continued to move in its holiday rhythm, largely unaware of the depth of the atmospheric trap. The paralysis of the city's transport systems began to take on a systemic character. On the George Washington Bridge and the Queensboro Bridge, several multi-car pileups occurred. Drivers simply could not see the brake lights of the vehicles in front of them in time to react. Traffic speed in Midtown Manhattan plummeted to 5 miles per hour, 8 kilometers per hour. Police officers at intersections worked in masks, yet many were forced to leave their posts due to fits of coughing and dizziness. The city was choking not just biologically, but logistically. By 11 a.m., the blanket over Manhattan reached its maximum density. The tops of the Empire State Building and the Chrysler Building were completely erased from the skyline. Residents on the upper floors of skyscrapers found themselves cut off from the ground by a sea of brown smog. While they were technically above the densest part of the inversion layer, toxic gases continued to cling to the sides of the buildings. This was worsened by the urban heat island effect. The city was generating its own heat, which helped anchor the smog layer to the surface of the earth. This visual and physical isolation began to change the behavior of the public. Streets usually filled with holiday shoppers started to empty as people instinctively sought cover. However, the air inside buildings was only marginally better than the air outside. The life support systems of the megacity were failing one by one under the weight of the atmospheric stagnation. You could watch the familiar world dissolve into the aesthetics of a slow-motion disaster. While the visual decay of the city was striking, the true tragedy was unfolding at a molecular level. Hidden within the brown fog, chemical processes were beginning to destroy the lungs and hearts of thousands of people. The city's blanket was rapidly becoming a funeral shroud for the most vulnerable members of the population. Reports from city hospitals by Friday afternoon began to show a terrifying trend that the municipal government could no longer ignore. The silent accumulation of the past 3 days was about to transform into a public health emergency of unprecedented scale. At 4 p.m. on Friday, November 25th, emergency admission logs at Bellevue Hospital began to show a statistically unusual surge in acute respiratory distress cases. The expected holiday slowdown never came. Instead, clinics were filling with patients who could no longer catch their breath. In a healthy body, the lungs act as a highly efficient filtration system. Air moves through the trachea into roughly 300 million tiny air sacs called alveoli. Here, oxygen enters the bloodstream while carbon dioxide is expelled. But the air over New York was no longer providing clean oxygen. It was delivering a concentrated mix of chemical irritants directly into the deepest parts of the lungs. The medical crisis was driven by two main processes. The first was the physical narrowing of the airways. The second was the chemical disruption of the blood's ability to carry oxygen. As people inhaled the yellow-brown haze, high levels of sulfur dioxide triggered an immediate defensive response known as bronchoconstriction. The muscles around the airways tightened in an attempt to block harmful particles. Under normal conditions, this reflex is protective. But in an environment with sulfur dioxide levels around 0.60 parts per million, it led to continuous oxygen restriction. For the elderly and those with conditions such as asthma or emphysema, this tightening of the airways often became the first step toward respiratory failure. By 8 p.m. on Friday evening, the effects were clearly visible inside Mount Sinai and St. Vincent's Hospital. Doctors were observing what is known as synergistic toxicity. Fine particulate matter, including soot and ash, acted as a delivery system for chemical irritants. These microscopic particles, often smaller than 2.5 micrometers, were coated in a thin layer of sulfuric acid. When inhaled, these particles reached deep into the lungs and caused localized chemical damage. This triggered inflammation and led to pulmonary edema, a condition where fluid begins to accumulate inside the lungs. Patients were, in effect, slowly losing their ability to breathe as their lungs filled with fluid. At the same time, the cardiovascular system was under severe stress. Carbon monoxide levels in traffic-heavy areas had reached between 20 and 30 parts per million. This gas interferes directly with the blood's ability to carry oxygen. When inhaled, it binds to hemoglobin far more effectively than oxygen does. As a result, less oxygen reaches the heart and brain. For someone with an already weakened heart, this created a dangerous imbalance. The heart was forced to work harder while receiving less oxygen. Later data showed that even moderate increases in this condition significantly raised the risk of heart attacks. By 10 p.m., the human cost of the event was beginning to rise, although it was not yet fully recognized. Hospital admissions for breathing problems were already above normal levels. But the most concerning pattern was not in hospitals. It was happening inside homes. Many of the most vulnerable individuals, especially the elderly, were dying without ever reaching medical care. In poorly ventilated apartments, often heated by high sulfur fuel, the air quality was even worse. Some died in their sleep, others collapsed during severe coughing episodes. Their bodies, deprived of oxygen and stressed by toxic air, simply could not continue. A closer look at the data revealed a clear pattern. The impact was not evenly distributed across the city. Lower income areas, particularly in parts of the Bronx and Harlem, showed significantly higher rates of respiratory distress. These areas had more residential incinerators and poorer building conditions. Air quality measurements in these neighborhoods remained at dangerous levels throughout the night. Doctors reported that patients were coughing up dark gray material filled with soot. This was a direct result of breathing air containing hundreds of micrograms of particulate matter per cubic meter. By 2 a.m. on Saturday, November 26th, the full scale of the crisis was still not understood by city officials. There was a delay of 1 to 2 days in collecting mortality data. While emergency rooms were overwhelmed with patients struggling to breathe, official records still categorized many deaths as routine heart failure or complications from seasonal illness. This was the phase of delayed recognition. The city was looking for a single, visible disaster. Instead, the smog was causing a slow and distributed crisis, affecting individuals across thousands of separate locations. The interaction of these factors created a silent but accelerating emergency. The airway constriction caused by sulfur dioxide, combined with the oxygen deprivation caused by carbon monoxide, acted as a multiplier of existing health problems. People who might have lived for years with chronic conditions were dying within days. By the early hours of Saturday morning, it is estimated that more than 100 people had already died due to the atmospheric conditions. Yet, the official alert level remained low. The air remained still, pollution levels remained high, hospital corridors remained crowded. The physical blanket over the city had become something more dangerous. It was now acting as a biological trap, disproportionately affecting the most vulnerable. As the sun rose on Saturday, the pressure began to shift. What had been treated as a temporary inconvenience was now becoming a political and public health crisis. City leaders were beginning to understand that this was not just weather, it was a system failure with lethal consequences. And the invisible deaths were about to become impossible to ignore. At 10:40 a.m. on Saturday, November 26, 1966, Mayor John V. Lindsay officially declared a first-stage alert for New York City. It was the first time in the city's history that such a measure had been taken. The political atmosphere was as stagnant as the air outside. Lindsay had been in office for less than a year. He was now facing a direct conflict between public health and the industrial systems that powered the city. Declaring the alert was not just a medical decision. It was a high-risk political move. The system responsible for air quality control in 1966 was limited and fragmented. The Department of Air Pollution Control had very little enforcement power. Its policies had long favored industrial growth over environmental protection. To trigger an alert, 3 conditions had to persist for at least 24 hours. Sulfur dioxide levels had to remain above 0.50 parts per million. The coefficient of haze had to stay above 5.0. And the National Weather Service had to predict at least 36 more hours of stagnant air. By Saturday morning, all 3 conditions had already been exceeded. At the center of the conflict was Consolidated Edison, known as Con Edison. It was the largest source of sulfur dioxide emissions in the city. Once the alert was declared, Mayor Lindsay demanded an immediate reduction in emissions. This required switching from high-sulfur coal and heavy fuel oil to cleaner energy sources. The problem was that the energy system was not built for rapid change. Company officials warned that reducing output too quickly could destabilize the power grid. They pointed to the risk of another large-scale blackout, similar to the one that occurred in 1965. The technical debate focused on a process known as load switching. Con Edison had the ability to import electricity from other regions. This would allow them to shut down the most polluting plants within the city. The mayor pushed for maximum use of this option. The company resisted. They cited the high cost of imported electricity and the strain it would place on transmission lines. The situation revealed a deeper tension. The same system that kept the city running was also contributing to its crisis. During the emergency response, the mayor also addressed the city's waste problem. He ordered a complete shutdown of municipal and residential incinerators. This affected tens of thousands of buildings that routinely burned garbage in basement furnaces. The reaction was immediate. Building managers warned that trash would begin to accumulate on the streets. The sanitation system was already under pressure due to the holiday weekend. The city now faced a difficult trade-off between visible waste and invisible pollution. A closer look at the existing air control regulations exposed serious weaknesses. Companies were allowed to exceed emission limits if compliance was considered too expensive. During the crisis, new proposals were already being developed. Officials began drafting stricter rules, including limits on sulfur content in fuel. At the time, most fuel used in the city contained between 2.5 and 3.0% sulfur. The proposed limits would reduce that number significantly. This created direct resistance from both energy suppliers and utility companies. By 2 p.m. on Saturday, the situation had drawn attention from the federal government. Agencies in Washington began monitoring the situation closely. Specialists were sent to the city with mobile equipment to verify pollution levels. This added another layer of complexity. Local, state, and federal authorities each had their own data and their own responsibilities. Coordination between them was slow and often inconsistent. Public reaction was also intensifying. The mayor's office received thousands of calls and messages from residents. People were no longer asking for information. They were demanding action. The discussion about air pollution was shifting from economics to basic public health. By 6 p.m., a temporary agreement was reached. Con Edison reduced output at several older power plants and increased electricity imports from outside the city. This lowered local emissions by an estimated 15%. However, the impact on air quality was limited. The pollutants already trapped in the atmosphere remained in place. The sky stayed yellow and heavy. Wind speeds remained at zero. The crisis revealed a critical limitation. The city could not quickly reduce pollution without disrupting its own infrastructure. Laws were outdated, technology was insufficient, and large industrial systems were slow to respond. The first stage alert had turned into a political confrontation. Even as officials addressed the public, health data continued to worsen. As night approached, attention shifted toward the weather. Officials and residents were waiting for a change in wind direction or the arrival of a cold front. But forecasts showed no improvement. The stagnant air remained in place. Reports that had once been ignored were now central to understanding the crisis. They described a system that had been vulnerable for years. The political struggle had reached a standstill, but the deeper failures were becoming impossible to ignore. The systems designed to protect the city had failed long before the crisis began. At 11:30 p.m. on Saturday, November 26th, barometric pressure at the New York Weather Bureau began to drop rapidly, from its peak of 30.20 inches, or 1,022 millibars. A powerful cold front, originating in the Canadian Shield, was moving quickly across the Great Lakes toward the Atlantic coast. This advancing mass of cold, dense air acted like a physical wedge. It slid beneath the warm, stagnant air that had been trapped over New York for the previous 4 days. By 1 a.m. on Sunday, November 27th, wind speeds at the top of the Empire State Building increased from 0 to 15 miles per hour, or 24 kilometers per hour. The stationary high-pressure system that had created the inversion was finally being pushed away. The clearing of a smog event is not gradual. It is a mechanical shift in the atmosphere. Meteorologists describe this process as frontal lifting. As the cold front moved in, it forced the trapped layer of polluted air upward. This broke the inversion layer that had been holding pollutants close to the ground at around 600 feet, or 183 meters. Once this barrier was broken, sulfur gases and particulate matter were carried into higher altitude winds. Their concentration began to decrease as they were dispersed over the Atlantic Ocean. By 3 a.m., ground-level temperatures had dropped to 38 degrees Fahrenheit, or 3 degrees Celsius. The physical transformation of the city was immediate. At 4 a.m., visibility at LaGuardia Airport improved from less than half a mile to more than 10 miles. The dense yellow-brown haze that had covered the city for 3 days was replaced by clear, cold air. Shortly before sunrise, rain began to fall. This introduced another cleaning process, known as washout. Water droplets collided with airborne particles and pulled them down to the ground. Much of the soot and chemical residue was washed into the city's drainage system. Despite all its infrastructure, the city remained dependent on a simple shift in weather for survival. As the sky cleared, the full human cost began to emerge. On Monday morning, November 28th, the Department of Health started analyzing mortality data. They used a method known as excess death calculation. This compares the number of deaths during an event to the expected average for the same time period. Under normal conditions, New York recorded about 220 deaths per day in late November. During the Thanksgiving weekend of 1966, the numbers rose sharply. Initial reports showed that 168 more people had died than expected between Thursday and Sunday. Most of these deaths occurred among individuals over the age of 65 and those with existing heart or lung conditions. Medical records showed a significant increase in cases of acute bronchitis and heart failure. This number was only a preliminary estimate, but it already indicated a mortality rate far above normal levels. At the same time, the city began assessing structural and economic damage. Officials estimated that the acidic air had caused millions of dollars in damage to buildings and infrastructure. Stone surfaces showed signs of erosion, and exposed metal components had begun to corrode. The economic impact was also significant. During one of the busiest shopping weekends of the year, businesses reported losses of around $5 million. In modern terms, this would be several times higher. A deeper analysis revealed a clear connection between pollution levels and mortality rates. The highest number of deaths occurred during the same hours when sulfur dioxide concentrations were at their peak, around 0.60 parts per million. The delay in the arrival of the cold front meant that residents had spent nearly 12 hours breathing heavily polluted air. The timing of the weather change likely prevented a far greater loss of life. If the inversion had lasted even one more day, the consequences could have been much more severe. By midday on Sunday, November 27th, the immediate crisis had ended. The sky was clear, but the city itself felt different. What had been seen as a temporary environmental issue was now understood as a systemic failure. The number 168 quickly became a symbol of that failure. It represented lives lost not only to weather conditions, but to policy decisions and industrial practices. The event was no longer just a local incident. It had become a national concern. Scientists and public health experts began using the data to argue for stronger environmental regulation. The conclusion was difficult to ignore. The city had been unable to control its own air, and the systems in place were not designed to respond quickly enough. As life returned to normal on Monday morning, attention shifted from hospitals to policymakers. The air was clean again, but the demand for long-term solutions was only beginning to grow. By December 1, 1966, the New York City Department of Health finalized its initial statistical review of the Thanksgiving weekend. The confirmed excess death count was 168 people. This number became a turning point. For the first time, the link between urban energy systems and public mortality was documented with clear and measurable data. The smog showed that air pollution was not just a local problem. It was a direct threat to public health that required action at the national level. At the time, environmental regulation in the United States was weak and fragmented. Local governments relied on limited rules and advisory systems with little enforcement power. Under the Clean Air Act of 1963, the federal government did not have the authority to set strict emission limits. The events in New York changed that. Data from the 168 deaths was used to push for stronger federal oversight. This led to the Air Quality Act of 1967. The new approach moved away from voluntary cooperation with industry. Instead, the country was divided into regions based on weather patterns and geography. New York was classified as a high-priority area. This allowed federal authorities to step in if local measures failed to maintain safe air conditions. At the same time, the city took its own action. In January 1967, New York passed Local Law 14. This law directly targeted the use of high-sulfur fuels. It required a reduction in sulfur content in fuel oil from about 2.5% to a maximum of 1.0% within 3 years. The law also required the shutdown of older coal-burning systems in Manhattan. This forced a transition toward cleaner fuels such as natural gas and low-sulfur oil. The technical and economic challenges were significant. Heating costs increased for many buildings. But the political reality had shifted. The city was no longer willing to accept health risks in exchange for lower energy costs. Despite these changes, pollution remained a broader issue. Air does not respect state boundaries. This led to further legislation at the federal level. In 1970, new amendments to the Clean Air Act introduced national air quality standards. These standards set clear limits for major pollutants across the entire country. To enforce these rules, a new federal agency was created in December 1970. This agency was responsible for monitoring air quality, conducting research, and ensuring compliance with environmental laws. Its creation marked a major shift. For the first time, environmental protection became a coordinated national effort. The long-term effects of these changes can be measured today. In 1966, sulfur dioxide levels in New York reached as high as 0.60 parts per million. In modern measurements, these levels have decreased by more than 90%. The dense yellow haze that once covered the city is no longer part of daily life. This history offers a clear lesson. Industrial growth must be balanced with environmental control. Monitoring the atmosphere is as important as managing energy production. There is also a deeper reality behind these numbers. The progress was not abstract. It came at a human cost. The 168 victims of the 1966 smog became an unintentional turning point in environmental policy. Their deaths forced a rethinking of the value of clean air. Today, air quality data is available in real time. Monitoring systems provide constant updates across the city. What was once invisible is now measured and tracked. New York has moved from a city trapped under polluted air to one that actively protects it. The story of the Poison City does not end with the clearing of the sky. It ends with a change in understanding. Air is no longer treated as an unlimited resource. It is recognized as a shared and essential part of human life. By studying how the city nearly failed, we now understand how to prevent it from happening again.